It's still on the order of few tens megahertz. So that means there is huge difference between them. Then you must wonder how we can bridge this gap with nowadays computational architecture. Actually, this is the solution. So nowadays, we utilize this kind of hierarchy memory architecture in order to bridge between the main memory and then CPU. So basically, main memory, the time to read and write information into main memory for each bit is about 50 nanoseconds, let's say. While for CPU, we know since its main clock frequency is a few gigahertz, so that means reading and writing takes less than 1 nanosecond. So in order for them to talk to each other, you have to build several levels of cache memories, level 2, level 1 cache memories, and then some very high-speed register memory, and then data goes from one layer to the next, and finally they reach to CPU, and then they come back in the opposite way. As you can imagine, this architecture actually, while it solves the problem, it still brings in some additional issues. For example, for data to go from one layer to the other layer, obviously this will take time and also cost energy. So basically it contributes to extra latency and energy consumption. So it will be ideal if we can directly talk to CPU. So basically if the main memory can directly talk to CPU, that would be the most ideal case. However, this is not very realistic given current device performance. But nowadays, with the development of some emergent memory architecture, memory devices, for example, magnetic memory, MRAM, magnetic random access memory, it makes it possible to simplify the memory architecture as shown here. For example, for MRAM, we know actually accessing time, for example, is on the order of 10 nanoseconds. And in some extreme cases, you can push it even below 10 nanoseconds. So it's very close to the performance, the speed performance of CPU. And at the same time, it also has a very small footprint. For example, it is one MTJ, one transistor design, one cell, one transistor design. So that can make the memory density quite high. So that means you can potentially make it a main memory. And finally, the energy consumption is also somewhere between the existing main memory, DRAM, and also those fast cache memory. So then that also gives you some hope to utilize it to be used as a high density, but also fast memory. But the problem is that it's still not there yet. So as you can see, this speed performance, about 10 nanosecond accessing time, is still much larger than the cache memory. So you can still not directly talk to CPU. So what's the bottleneck? So why can we not write information very quickly into those magnetic memories? Actually, it turns out that it's governed by some very fundamental physics laws, as explained by this curve. So in this figure, the y-axis is the switching current, while the x-axis is the switching time in log scale. So basically, -8 corresponds to 10 nanoseconds, and -9 corresponds to 1 nanosecond. So as you can see, as you reduce a switching time below 10 to -8 second, 10 nanosecond, actually the switching current becomes significantly large. Yes?
The idea of a loop of current producing the magnetic moment.
So you mean how?
I'm trying to map current on the spin.
Yeah. I will explain it probably in the next slide. But here, we can at least see that there is a very sharp increase in the switching current as you reduce the switching pulse width. So this actually turns out to be governed by some very fundamental physics law, that is angular momentum conservation. So why do I say this? Why the switching of magnetic moment is governed by angular momentum conservation? So actually, it has something to do with the nature of magnetism. And we know magnetism actually is nothing but just angular momentum. Actually, this was first discovered, verified by Einstein a long time ago. And people say this is probably the only experiment that Einstein has ever done. So basically, what he did is that he tried to magnetize a magnetic block, a bar. And he found that while you magnetize this magnetic bar using those coil, this circuit coil, he found that actually while the magnetic moment gets switched, the physical piece of this magnetic block, it also gains some angular momentum. That means it starts to rotate. So that means in order to switch the magnetic moment, it has to gain some angular momentum from somewhere else. In this case, it gains the angular momentum from its physical rotation. So in the end, the total angular momentum is conserved, including both the magnetic part, also the physical, the motion part. So basically given this, that means if we want to switch the magnetic moment, actually we have to satisfy the requirement of angular momentum conservation. And in order this spintronic device actually is satisfied this way. So basically we have one layer of magnetic material which acts as this information storage layer. So its orientation can be pointing to the left or pointing to the right. In order to switch its orientation, what we do is we can apply a current across this kind of tri-layer structure, which is known as spin wave or magnetic tunnel junction. So in the current, when electrons that go from the bottom magnetic layer to the top magnetic layer, actually the conduction electrons will carry spin, which originally reside on the bottom layer and then into the top layer. And when the conduction electron goes from the bottom to the top, their spin orientation will get flipped. And finally, they will be aligned along the local moment direction with the top magnetic layer. So during this process, the conduction electrons will lose their spin angular momentum. And correspondingly, the local magnetic moment on the fixed layer, on this second magnetic layer will gain angular momentum. You can imagine if you push enough electron spin into the top layer, you can flip its orientation. So that is how the magnetic moment gets switched in this spintronic device. So in this process, as we said, the angular momentum has to be conserved. That means in order to switch this magnetic moment of the second layer, you have to push enough spin into the top layer. Or in other words, you have to apply large enough spin current. So that's the reason why when you reduce the power switch, in order to keep the total angular momentum conserved, you have to pump more spin current into it. So that's the reason why the current density actually increases inversely proportional to 1 over T, where T is the power switch. So basically that's the main reason why we cannot switch magnetic memory very fast these days. However, although this is governed by the fundamental law of angular momentum conservation, you can also imagine if you do not have much angular momentum to start with, if the magnetic layer itself does not carry too much angular momentum, then you can make it flat, yes.
So that's for one electron spin?
This is for all of the spin ensembles inside the magnetic layer.
Of current size. Okay.
Yes, so you apply this much current and then switch all of the spins together in the magnetic layer. So one possibility to reduce the switching current at a very short power switch is to make this flatter. So how do you make it flat? Well, the way is to make the total angular momentum lower. So if your magnetic layer only has a very small amount of angular momentum to start with, then you can imagine you do not need to put too much spin current inside in order to switch it. So actually that's the main topics that I'm going to discuss today. So how we can lower down the angular momentum inside magnetic layer in order to reduce the switching current. So now if we look into the available magnetic materials and ask which material has low magnetic moment or low angular momentum, but at the same time can still have finite spin polarization. The reason that we like finite spin polarization is because that is something that we rely on reading and writing the information from the magnetic layer. So first of all, we know, of course, most traditional magnetic material for spintronic device is this ferromagnet. And for ferromagnet, we know that it has finite magnetic moment. At the same time, it has finite spin polarization. But in order to reduce the magnetic moment, then naturally we can think of antiferromagnet. And we know antiferromagnet, you have two spin stabilities, and those two spin stabilities, actually, they will cancel out with each other in terms of net magnetic moment. At the same time, the spin polarization, we know, is also 0. So it's probably not very useful. And finally, we also know there is ferromagnet, which has random orientation in the spin. And so it gives rise to 0 moment, but at the same time, 0 spin polarization. By the way, here I can give you a better definition of what spin polarization is. The spin polarization is basically the difference between the spin up and spin down electrons. Okay, so now what's our solution? So how can we find a material which has 0 moment, but at the same time has a finite spin polarization? So that's the main goal of my today's talk. So mostly I will solve the problem how we can utilize those kind of 0 moment magnet to realize efficient magnetic reading and writing. And towards the end, I will show you how we can possibly combine those magnets with topological insulator to realize efficient, energy efficient magnetic switching. Okay, so now let's get back to the antiferromagnets that we talked about a little bit earlier. So as we said, antiferromagnet has two spin stabilities, and those two spin stabilities will cancel out with each other. It leads to a 0 net magnetic moment. So there are quite a lot of advantages associated with those materials. For example, because your moment is 0, so there is no stray field from those magnets. Then you can imagine you can bring two magnetic devices very close to each other without worrying about the interference between those two magnetic beats. Also, people know that actually the magnetic dynamics is very fast inside antiferromagnet, so you can realize terahertz magnetic dynamics. But the disadvantage associated with antiferromagnet is since the spin polarization is 0, so how do you read and write information from those materials? Or in other words, in a simple word, how can you even define those two different states, 1 versus 0? So which state is 1, which state is 0? So it's not obvious to us. For ferromagnet, obviously you can define spin up as 1 and spin down as 0. But in this case, you have spin up and spin down at the same time. How do you define the two different states? At the same time, we can also consider another group of magnetic materials, which is ferrimagnet. It also has two spin stabilities, and those two spin stabilities also antiparallelly coupled with each other. But the difference between those two groups of materials is that for ferrimagnet, the two spin stabilities are composed of different atoms. For example, spin up is composed of atom 1, and spin down is composed of atom 2. And those two atoms can be different chemical element, or they can just occupy different crystallographic locations. So basically, the main difference between those two materials is that this one has a lower symmetry. So while this one, the spin up and spin down atoms are exactly the same, in this material, spin up and spin down atoms are slightly different, although their spin are antiparallel with each other. Actually, I will show you with this group of materials, it's much easier to realize electrically induced switching and detection. Why? Now let's review what we learned from solid state physics. We know through our solid state physics study, we know actually for materials there are properties which mostly reflect the Fermi surface property, and there are also properties that's directly related to the Fermi sea. So for example, we talk about magnetic moment or magnetic susceptibility, and we know actually that property comes from the whole Fermi sea. If you want to calculate the total moment of a certain material, you have to integrate over all of the density of states below the Fermi level. So basically, it's a Fermi sea property. At the same time, there are also properties that is only related to the Fermi surface. For example, most of the transport properties are only sensitive to the Fermi surface. For example, we know if we talk about the tunneling magnetoresistance of a certain device, actually it's proportional to the spin polarization. of the two magnetic layers you utilize. And the spin polarization here is actually only defined as the difference of the density of states at the Fermi level. So it has nothing to do with what happened below the Fermi surface. Okay, so now knowing this difference, we can potentially design such kind of material system which has zero moment. Well, in order to reach zero moment, you just make sure that the integrated total number of states below the Fermi level are the same between up and down band. At the same time, you can still ensure that there is a finite spin polarization at the Fermi level. For example, here, the density of states for spin up is much larger than the density of states for spin down because of this asymmetry. If you can compare this with the antiferromagnet case, because as we said, for antiferromagnets, there is a very high symmetry. So basically, spin up and spin down are completely the same, no matter which specific energy you talk about. So at the Fermi level, you have the same number of spin up and spin down electrons, and for each of the other different energy, you also have the same number of spin up and spin down electrons. So that's the reason why in antiferromagnet, you have zero moment as well as zero spin polarization. But for ferrimagnet, you can have zero moment, but at the same time, you can have finite spin polarization at the Fermi surface. And this finite spin polarization will allow us to read out the information easily from the material. Okay, so what kind of system can we utilize in real life to realize such kind of property? So here, actually, we utilize this kind of alloy system that has been studied for quite a long time, which is a transition metal rare earth alloy. Just to give you an idea where those elements are located in the periodic table, for transition metals, actually, we are talking about those three elements, iron, cobalt, nickel, because those are the most traditional ferromagnetic elements. And then for rare earths, actually, we are talking about elements that is located here. And particularly today, we are talking about terbium, which is this 4F rare earth element. So people already know that actually if you make an alloy out of those two different type of elements, actually they will naturally be aligned antiparallel with each other in terms of their spin due to the exchange interaction between D electrons in cobalt and F electrons inside terbium. At the same time, because rare earth elements, their magnetism mostly come from 4F electrons, so, but their 4F electrons at the same time is also very far away from the Fermi surface. Actually, fewer electron volts below the Fermi surface or above the Fermi surface. So that means across the Fermi surface, only the transition metal here, the cobalt, actually dominate over the density of states. So actually, if you measure it electrically through the transport property, actually it mostly reflects the cobalt spin orientation. So that's how you can reach a system that has almost zero moment, but at the same time has finite spin polarization. Actually, this is exactly what we observed in our experiment. So in our experiment, we make alloy out of cobalt-terbium with different composition. So from left to right, we have more and more terbium inside. So here we have 13% of terbium. Here we have 29% of terbium. As you can see, for a certain concentration, for example, here terbium about 21%, we get zero net magnetic moment. So this line, this row actually is a magnetometry study which reflects the magnetic moment. As you can see, the magnetic moment reaches zero at certain concentration. But at the same time, if we measure the electrical property, which is a anomalous Hall effect, you can see that even when the moment reduces to zero, you still have finite Hall resistance. So that means you have zero moment, but a finite transport related property. And you can utilize this transport property to tell whether the material is located in the state 1 or state 0. And here state 1 can be defined as cobalt pointing up, and state 0 defined as cobalt pointing down. And terbium is just chosen the opposite direction with cobalt. Room temperature, yes. And also you can see that the moment variation is summarized in this figure. As you can see, the moment goes to zero and increase again. That is because on this side, the terbium moment actually gets larger and they start to dominate. But for the Hall resistance, actually they never reach 0. They always keep a finite value. Okay, so next question. Here we show that we can read information from such a zero moment system. The next question is, how do we write information inside? How do we switch its orientation? So as I discussed earlier, one way to switch the magnetic moment orientation is to utilize this kind of spin wave or tunnel junction structure and rely on the spin transfer torque, utilizing the polarized spin from another magnetic layer to switch the magnetic moment of the second magnetic layer. But today I'm going to utilize another mechanism, which is known as spin Hall effect. A spin Hall effect was discovered about 4 decades ago, where people demonstrated that when you apply a current inside a material with strong spin-orbit coupling, actually you'll find that spins will get deflected towards different directions, and they will accumulate at different surfaces. So basically, this gives us a mechanism where we can generate spin current out of a longitudinal charge current. A few years ago, I demonstrated that basically we can utilize those spin Hall effect inside heavy metals, for example here tantalum, to switch the orientation of adjacent ferromagnet layer. So basically you apply current in the heavy metal layer, and then through the generated transverse spin current, you can switch the orientation of this bottom free layer, either to make it in the anti-parallel states or the parallel states. So now you have these different resistance states due to the switching from the spin Hall effect of the heavy metal layer. So today we are going to utilize this same effect, but onto the zero moment system. So this is a material, this is a device that we made. So the bottom layer is still tantalum, which provides the spin Hall effect or the spin current. And then on top of it, we have this Cobalt-terbium alloy, which we try to make it zero moment. So we tune the concentration, so the magnetic moment is almost 0. So again, this is a magnetometry study where you see that the magnetic moment is almost 0. But at the same time, we apply a current inside this tantalum layer and utilize the spin Hall effect inside tantalum layer to switch the orientation of this Cobalt-terbium moment between those two opposite states. As you can see, by applying current, which is the x-axis, we can switch the nominal Hall resistance from the high state to low state, or switch it backward by just simply flipping the current direction. So far, we show that by utilizing such kind of zero moment magnet, Cobalt-terbium, we can realize both magnetic reading through the nominal Hall resistance, as well as magnetic writing through the applied charge current. Okay, so this is the first step, because we remember our goal is to realize fast magnetic memory. And here, at least, we show that at least we can read and write information into those magnetic materials. The next step is to show that there is some speed advantage associated with those zero moment magnet. So how are we going to show the speed advantage? Well, there are two possibilities, actually. The first one is to show the switching a single bit magnet. So basically, you make the magnetic device into a single domain. So that usually requires that you have to make the device below 10 nanometers. At the same time, you use picosecond or maybe hundreds of picosecond powers to switch it. And then show that this switching speed is faster than previous magnetic device. Another possibility is, instead of looking at this kind of tiny device, we can look at a much larger device, which is micron size. And in those micron size device, we know usually it's multi-domain. For multi-magnetic domain, we know actually the switching mechanism is usually due to domain nucleation and domain propagation. So the advantage of this type of measurement is that now you can make a much larger device. So the requirement on nanofabrication is much lower. And secondly, you can use nanosecond powers instead of picosecond powers to show the speed advantage. So this is a mechanism, this is approach that we are going to utilize today to show the speed advantage. So basically what we do is we utilize the same spin Hall effect, the electrically induced magnetic switching mechanism, instead of to switch the moment altogether, but to push the magnetic domain wall. So basically, if we can show that the magnetic domain wall moves at a faster speed compared with the previous magnetic materials, then we can also potentially argue that those zero moment magnet does have faster switching speed. So how do we observe those magnetic domains? The methods that we utilize here is a magneto-optical Kerr effect microscope. So if you are not very familiar with Kerr effect, you might have heard about Faraday effect, magneto-optical Faraday effect. In magneto-optical Faraday effect, when the light, circular polarized light, goes through a magnetic material, depending on its circular polarization, the left circular polarized light and right circular polarized light will be absorbed or reflected differently by the magnetic material because of the optical selection rule. Then you can imagine if you start with a linearly polarized light, which can be decomposed into left and right circular polarized light, then the outgoing light will have slightly different circular polarization. So originally it might be polarized at 45 degrees, but after it comes out from a magnetic material, its orientation, its circular polarization, its linear polarization might be at, let's say, 47 or 48 degrees. So through that rotation of the circle of a linear polarization, we can know whether the magnetic moment is pointing up or pointing down. So actually, by utilizing a magnetic optical Kerr effect microscope, we can clearly see the domain structure inside a micron-sized sample. So this is still cobalt-terbium alloy with its moment close to zero, but you can still see that there are brighter or darker domains. And the brighter domains actually correspond to cobalt pointing up, and the darker domains correspond to cobalt pointing down. Again, here, similar to the transport measurement, the optical signal is also mostly dominated by cobalt. The reason is for photon spin interaction, actually, they also have some selection rule. It's not integration over the whole, over all of the spin states. It's only selectively sensitive to spin states that is located at a certain energy level. So that's the reason why when we measure the Kerr effect signal, we can still recognize those two different domains, although the net moment is very close to zero. Okay, so now what we do is we apply a sequence of current pulses, nanosecond current pulses, onto those micron-sized wires. And what we saw is that actually the domain edge will get pushed by those current from left to right. So after each pulse, we record the magnetic texture image, and we can track the location of those domain wall edges. And by summarizing the relationship between the domain wall position and then apply the pulse width, we can calculate what is the domain wall velocity as a function of applied current. As you can see, across different compositions of cobalt-terbium alloys, we can get different slopes that reflect different velocity of those domain wall speed. And finally, if we summarize the domain wall mobility, which is defined as a slope of those curves, you can find that there is one specific position, specific composition that has fastest domain wall velocity. It turns out that actually that one corresponds to the one with zero net angular momentum. So by using this multi-domain device, we demonstrated that actually there is some speed advantage associated with those materials with zero net magnetic moment. And if you compare those with traditional ferromagnetic material like cobalt or cobalt iron boron, you will see that there is at least a factor of 5 improvement in the domain wall speed. So far, we show that we can electrically read and write information into this zero moment magnet. At the same time, those zero moment magnet does switch faster compared with high magnetic moment materials.
So when you say switch faster, how does it compare to your target of terahertz or gigahertz or something? Like we're like a factor of 5 on the way to 3 orders of magnitude? Or
Yes.
I mean, I'm not trying to be critical. I'm just trying to understand kind of how that sets in comparison to the
Yeah, so it's, well, since we did the experiment in those kind of multi-domain device, so it's very long propagation distance. So actually, you realize those kind of micrometers movement, we have to apply nanosecond pulses. So it's not terahertz. No. No. So another reason that those materials are not extremely fast is because there is terbium inside, which is rare earths, and rare earths usually have very high damping. So that one also lower down the speed of the magnetic switching. So based on simple argument, if you can make a nanometer size device out of those materials, I think the switching time will be, let's say, 100 or around below 100 picosecond. But we just didn't make that type of device.
Thank you.
Okay, so far I showed that how we can realize magnetic reading and writing in those zero moment magnet. The next task is to show whether we can make this type of material better. As I mentioned, actually rare earth transition metal alloy has some disadvantage. One thing is that there is a usually very high magnetic damping, which dissipates energy significantly. The second problem is that rare earth is very difficult to deal with. I don't know if you have ever worked with metallic rare earths. Well, for rare earths in the metallic state, actually they are very easy to be oxidized. So even if just simply exposed to air, they will turn into oxide within seconds. So another thing is that they are have very bad temperature stability. So when you change the temperature, actually their magnetic property will change significantly, and sometimes it's even irreversible, meaning if you go back to room temperature, they do not keep their original property. So basically we want to get rid of the rare earth element. So how are we going to do it? Well, we turn our attention to another system which can also have zero moment, but it's composed of other elements and not rare earths. Basically, this type of material is known as Heusler alloy. And Heusler alloy is basically composed of, in general, 3 different elements, X, Y, and Z. And for X and Y, basically they are transition metals, for example, cobalt, iron, vanadium, manganese. And for Z, actually they are group 4, group 5, or group 3 elements like gallium, silicon, aluminum, etc. So when you make this kind of Heusler alloy, it turns out that it can also form some ferrimagnets whose magnetic moment can be tuned almost equal to 0. Actually, people even summarized some very simple rule to determine what is the net magnetic moment out of those Heusler alloy. The rule is that you simply count how many valence electrons exist in a chemical formula. For example, if you have manganese 2, palladium 1, and gallium 1, if you add all of the valence electrons inside this formula, if it's equal to 24, you need to have 0 moment. If it's above 24, then basically you have positive moment. And if it's below 24, you get negative moment. Here, positive and negative means whether it's moment governed by one spin stabilities or the other spin stabilities. So now the goal is how we can design a material which has its valence electrons almost 24. Actually, people look into this type of system like manganese 2, platinum, gallium. And they found that actually by varying the concentration between manganese and platinum, and you can bring the total moment almost equal to 0. So for example here, X goes from 0 to 1, and you can see the magnetic moment goes to 0 when X is about 0.6. So you have 0.6 platinum and 2.4 manganese within the same chemical formula. Actually, this was studied a few years ago by Claudia Heusler group. So, and also at this point, when the moment is very close to 0, actually you have divergent in the corrosivity, as shown here. We look into a system that is slightly different, which is also studied earlier by another group in Ireland. And basically what it shows is that in this compound, which is manganese 2, ruthenium X, and gallium, the magnetic moment is mostly contributed from 2 manganese sublattice. And But those two manganese lattice, they are different because one manganese, their closest nearest neighbor is gallium, but for the other manganese, their nearest neighbor is ruthenium. So in terms of their crystal location, actually those two manganese are not completely equal to each other. So it also has reduced symmetry. So that's the reason why it's a ferrimagnet instead of antiferromagnet. What people found is that if you make intentionally some ruthenium vacancy in those materials, actually you can tune the Fermi level of this system. And if you adjust the ruthenium concentration correctly, you can finally put the Fermi level in a certain position so that spin up and spin down bands are equally occupied. So in the end, you have net zero net magnetic moment. But what they also argue is that in this specific case, actually the Fermi level will fall into the gap of the minority band. So that means actually you have 100% spin polarization at the Fermi level. So it's half matter. So at the Fermi level, you only see one specific type of spin. So this would be ideal because you have two promising properties. One is zero moment, and the other is 100% spin polarization. So originally, you would think that this is probably controversial, but actually, it is really possible to be realized in this type of system. So basically, our goal is to utilize this type of ferrimagnet and show that we can also realize magnetic reading and writing. So we try to repeat those works by first depositing manganese, ruthenium, gallium on top of single crystal MgO substrate. So here we utilize magnetic sputtering, magnetron sputtering to grow manganese, ruthenium, gallium onto the substrate. As you can see that actually we can realize almost epitaxial growth using this technique. And then if we do the magnetometry study, we will find that actually as we tune the concentration of the ruthenium element, actually the magnetic moment will go from high to low and goes high again, as is summarized in this figure. So as you vary the concentration of ruthenium, the net magnetic moment goes from some high number to close to zero, and then to some finite number again. So this indicates that we can reach a state that has almost zero net magnetic moment. And then we also verify that you can still observe some transport property, like the normal Hall effects in those nearly compensated states. So the normal Hall resistance is finite. And also we can utilize the spin orbit torque or the spin Hall effect to realize electrically induced switching between those two different states in this nearly compensated ferrimagnet. So far we realize magnetic reading and writing in a second compensated ferrimagnet system. And in this case, it's a Heusler alloy, which is based on manganese element. Okay, so my last topic is related to topological insulator. So I would like to show that how we can combine those low moment or zero moment magnet with topological insulator and then realize room temperature topological insulator induced magnetic switching. So why are we interested in topological insulator for magnetic switching? The reason is, as I discussed, in today's talk, actually we only focus on spin Hall effect for magnetic switching. So spin Hall effect is you apply a longitudinal charge current, and then you generate some transverse or vertical spin current. And this is an intrinsic property of materials. You may naturally ask, what material has the strongest spin Hall effect? If you want to get very efficient spin current generation, so what material should we look into? So we can make some hand-waving argument that topological insulator is probably the material with the strongest spin Hall effect. The explanation is like this. So we know there is Hall effect and there is quantum Hall effect. So basically, quantum Hall effect can be viewed as an extreme version of the classical diffusive Hall effect. And similarly, we know there is spin Hall effect and there is also quantum spin Hall effect. And to some extent, the quantum spin Hall effect can be viewed as an extreme version of the diffusive spin Hall effect. And you can easily extend the 2D quantum spin Hall effect to the 3D topological insulator case, where you have spin momentum locked surface. And then you can naturally imagine that topological insulator will probably give you the strongest charge to spin conversion efficiency. Actually, this was proved a few years ago in those experiments, where people demonstrated that actually at a very low temperature, 2K or 4K, you can utilize the surface states of topological insulator to switch some low temperature magnetic materials. And here actually is some magnetically doped topological insulator. So it's bismuth, antimony, telluride. So people show that by applying current inside the topological insulator, for example, bismuth, antimony, telluride, you can switch the magnetic moment orientation in this magnetic layer. However, those experiments are only done at very, very low temperature, as I said, 2K or 4K. The question is it possible to push this effect to room temperature and then realize some more practical spintronic device? So that's our goal. So basically, we try to integrate the zero moment or low moment magnets that we developed earlier, like cobalt-terbium alloy, with the topological insulator, bismuth selenide. And here, the bismuth selenide is grown by MBE in Penn State. And then they ship the sample to our lab, and then we remove the capping on top of the topological insulator, and then put down the cobalt-terbium alloy. And then we can verify that the cobalt-terbium growing on top of bismuth selenide still have relatively low magnetic moment, although it's not completely compensated. It's a low moment, and it has a perpendicular anisotropy, which is preferred. And then we pattern the material into this kind of Hall-bar structure, and then we can apply current through this bismuth selenide and cobalt-terbium bilayer structure, and then at the same time measure the enormous Hall resistance. As you can see here, when we apply a current in the positive direction, we switch it to the positive Hall resistance. Then when we apply a negative current, we switch it to a negative Hall resistance. So basically, this shows that we can utilize topological insulator to realize magnetic switching in this kind of low moment ferrimagnet. What about the power performance? If you compare those topological insulator like bismuth selenide or bismuth antimony telluride in terms of energy consumption for switching each bit, we can compare them to platinum and tantalum. As you can see, there is order of magnitude improvement in terms of power consumption. So it does lower down the power required to switch those moments. The reason is the switching current is much lower. Again, because topological insulator has very strong efficiency in converting charge current into net spins. Okay, so basically today, my topic is mostly about how to realize magnetic reading and writing with some zero moment magnet. Particularly, I talk about the concept of compensated ferrimagnet. So similar to antiferromagnet, compensated ferrimagnet has zero moment. So you can make a very high density and high speed spintronic devices out of them. But at the same time, it allows easier reading and writing operations compared with antiferromagnet, because on the Fermi surface, you have non-zero spin polarization. And finally, we also look into Heusler alloy as another potential candidate for compensated ferrimagnet. And we also show that using topological insulator, we can potentially combine low switch energy together with the fast switching dynamics that is obtained on those zero moment magnet. So thank you for your attention. Let me know if you have any questions.
So now we are open to questions.
Yeah.
You said with the magnetic memory is sort of holding up if you want to make a humongously large CMOS